Good morning. I'm Scott Arnold, Senior Manager of Publications and Standards for AMCA International. Welcome to Advanced System Effects, Causes and Remedies. In preparing this session, AMCA met the standards and requirements of Registered Continuing Education Program, or RCEP. RCEP's involvement should not be deemed or construed to be an approval or endorsement of the content of this session. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. This session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. Now, with that out of the way, let's meet our presenters. Adam Habegger is Product Solutions Engineer, Metal Centrifugal Fans for Hartzell Air Movement. A seasoned sales and market engineer, he specializes in industrial ventilation, pollution control, pulp and paper, automotive paint line, oven ventilation, and processing industry applications. He holds a bachelor's degree in mechanical engineering from Michigan Technological University. Joining Adam is Justin Meyer. Justin is an applications engineer for Hartzell Air Movement. Since joining the company in 2011, he has held several key roles, including test engineer and project engineer. With a strong background in engineering and product development, he brings over a decade of hands-on experience supporting custom fan solutions across a range of industrial applications. He holds a bachelor's degree in engineering technology from the University of Dayton. First up is Ryan Cassel. Ryan is fiberglass product and market manager for Hartzell Air Movement. A market manager since 2016, he specializes in water and wastewater, metal plating, pulp and paper, and food processing applications. He holds a Master of Business Administration degree from Malone University and a Bachelor of Business Administration degree in Finance and Management Information Systems from Ohio University. Ryan?
Thank you. Hello, everybody. So the purpose of this presentation is to provide a better understanding of the mechanical consequences that can happen from when systems are designed with non-laminar airflow or system effects. Examples will be shown on how just accounting for system effects through additional pressure calculations can be both a safety hazard and a mechanical nightmare. Actual real-life examples will be discussed, showing unforeseen effects of system effects when design principles are not followed or aspects of fan limits are overlooked. The impacts of temperature changes will also be talked about, from cold start to actual, why it's important, and holding flow or pressure constant and how that can affect fans' operation. So as an intro, exhausting and or supplying air in systems can be very simple. Achieving a near uniform airflow, laminar, in a system is key to lowering a fan's energy usage. Rookie mistake. Energy usage, reducing its wear and tear, and minimizing maintenance headaches. But once ductwork is extended and duct elements are added, systems can become quite complex. Types of the fan manufacturer, as a fan manufacturer, we are not system designers. We are equipment manufacturers. But most often, the number one symptom of a system not working is a fan not working. Types of systems discussed will be more complex single fan layouts. We'll be talking about multiple fans running in series, multiple fans running in parallel, combination of fans running in parallel or series, and systems programmed to hold pressure or flow constant. So initially what I want to do is just have some definitions of what we're going to be talking about today, just so there's an understanding. But an air system, an assembly of duct, filters, conditioning devices, dampers, louvers, fans, etc., and the like, the main purpose of which is to move air from one place to another in a controlled fashion. Most draw air from one space and discharge into another. System effects, per AMCA, change in system performance resulting from interaction of one or more system components. You've got resistance element factors used in the designs. Only indicates effect of the system configuration on a fan's performance. And you've got two or more elements such as elbows. You've got T and elbow and damper in close proximity. When you have that, air entering the second element is highly turbulent and asymmetrical in profile, and that causes higher than expected losses and can significantly impact the fan's operation. Fans operating in parallel. Shown here a couple of examples. Fans in parallel will handle the same amount of system resistance, but share portions of the volume airflow. Fans in series. So fans in series will handle the same volume of airflow, but share portions of the system resistance. Examples shown, one fan feeding into the next fan. And key aspects here is higher negative pressures and/or airstream temperatures require fans in series to operate at slightly different RPMs. And the effects of system effects. So some of the effects are going to be poor fan inlet and outlet conditions, more than just system effect losses though. Most systems have system effects in their design. I mean, that's kind of a known. You're going to have some. And that cause the fan to not perform as intended. You know, problems manifest in the form of mechanical failures, increased maintenance costs, underperformance, higher operating costs, and safety issues. And then system design per AMCA. You know, AMCA does have the, I believe that follows this class, the troubleshooting. But system design should minimize needed troubleshooting. Some of the items that will be listed, such as noise, too much or not enough airflow, high static pressures, power consumption higher than nameplate. You can have high levels of vibration, premature failure of the motor, bearings, wheel props, and problems in a system can have many symptoms and many adverse outcomes. And example one, I'll turn it over to Justin.
Thank you, Ryan. Good morning, everyone. Our first example is a general exhaust application from a large manufacturing building. The system consists of multiple centrifugal fans operating in parallel. The fans are connected to a common header, which runs underneath in this picture into the building to pull the air out through a bunch of branches, and then the fans simply exhaust atmosphere. The fans are VFD operated and sequenced to maintain a constant pressure inside of the main header, and that's how they're controlling their that's how they're controlling their system, or controlling the fans. Then the airflow rates are controlled with dampers that are inside of each branch. So what you see here is a very good, well-designed inlet and outlet onto each of these fans. Nice long straight run of ductwork into the fans. Nice long straight run of ductwork out of the fans. The challenge that we ran into in this example is that we had inadequate airflow rates and also high vibrations through the fans reported during the commissioning of these fans. So we get called, fans aren't doing what they're supposed to do, so we go to site, we do our kind of typical troubleshooting. So we look at the fan installation, check for binding, poor duct connections. These fans were sitting on concrete field inertia bases, so we check the bases, check the snubbers, make sure nothing's short-circuiting or binding in the system. Walk the system, look for any obvious signs of obstructions, leaks, or anything that could cause poor airflow at the inlet of the fans. And then we start asking questions. How is the system being operated and how are the measurements being taken? So what we found out is because of the construction schedule, this entire system wasn't being commissioned at one time. They were trying to commission the fans in groups at a time. And the ductwork in the entire system wasn't even complete yet. So what the contractor was doing is they were, inside the main headers, they were installing dampers to apply a false load to the system to maintain their constant pressure. And then the fans were being manually started and brought up to speed. to the speed required to maintain that pressure. But the header pressure was being held consistent, but due to the dampers being undersized, the airflow rate was low, and it caused the fans to operate near a stall condition. So because of the system layout, the first 2 or 3 fans in the system would have enough airflow, and then you would start to starve the fans later down in line. So if we look at this on a fan curve, you see the black static pressure curve. That blue parabola in there is the assumed system curve, and that shows where these fans were designed to be operated at. The red parabola shows our stall point, and because these fans were being operated at a constant pressure, the system was being operated along this horizontal green line that you see. So depending on what the airflow requirement was for the system, the fan speed was being changed in order to meet their requirement. So what we see here is with the smaller dampers installed, the fans didn't need to operate as fast, and they were actually operating at stall point. So that's why they had the high vibration, the low airflow rates.
So the second example we have is going to be a wastewater odor control application. The performance, we had 2 arrangement 8 centrifugal fans that are running one at a time. So they have one standby on a direct drive VFD. And some of the key aspects to keep in mind is after commissioning, it was the first 6 months, there were noticed some issues, but there was high vibration switches on the fans, and they would rotate the fans over a 2-week schedule. System layout. So what you see there on the bottom right is an elbow coming into a branch that is feeding down into the fans. There's a filter box past that branch, inlet box, and so on, and then into the fans. Fans operate between biological scrubbers and carbon absorbers. And basically, the layouts of each fan mirrored each other except for this split immediately upstream where that elbow is, so, and downstream. But they basically, afterwards, they merge again up into a header, the airflow does. So some of the background, the fans were balanced BV4 levels originally at the plant. Fans were installed 2 years prior to startup. So this is during COVID timeframe where things got installed and then there was kind of a waiting cycle. Part of the problem is there was no maintenance done on the fans. Air permits required exact airflow over a rotating 24-hour period, which is very, very difficult to do. And then system pressures were less by 7.5 inches versus the what they were designed for, reducing the speed from about 83 to 84% of nameplate. The site challenges, number one, airflow permit. Owners programmed the VFD to make real-time adjustments to achieve the exact airflow over a 24-hour period. That can cause problems, when that's being done. Accuracy of airflow readings. They had poor operation and maintenance, really lack of maintenance. High and oscillating vibration. And then we also had extreme noisy fans and equipment. Frequent vibration trips, a fan 1, and then a fan 1 failure. Troubleshooting steps we performed were to verify the actual operation of the fan curves, check the fan-to-fan, changeover routines, VFD history, looking at the airflow, hertz, amps, etc., CFD airflow analysis, and then we did field evaluation of fan 2 and a field evaluation of fan 1, pre and post rebuild. So the VFD and CFD analysis, what did it show us? Fan 1 and fan 2 operated at different speeds to achieve the airflow, and fan 1 appeared to be less stable. CFD analysis showed that fan 1, 75% of the airflow would enter one quadrant of the wheels. Fan 2 was slightly better, but fan 1 definitely had non-laminar airflow hitting 25% of the wheel. Fan 2, we started with fan 2 since it's the one that was in operation as far as troubleshooting. We looked at the installation. It was rigid mounted. We checked for binding in that mounting. Bearings, there was lack of maintenance done, so the bearings were replaced as there were some flat spots. Laser alignments were confirmed and redone. Coupling clearance was checked and verified, and then the wheel balance was checked and verified, and all those other 3 checked out. So vibration readings from 70 to 90% speed, we would jump it up 1 to 4% increments depending on if we started finding something. At 84% and above, what we found is that's when the vibration horizontal non-drive-in started really creeping up to a do not run zone. So you can see on that picture where it's red on the bottom left, we started seeing elevated vibration levels. The vertical non-drive-in levels would oscillate between 0.2 and 0.34 inches per second over 15-second increments, which, the oscillating vibration is hard to diagnose, and but it showed, whenever you have oscillating vibration, you have to really dig in. They did have vibration disconnect switch, but what I would say to those is they're a one-direction vibration switch. So depending on where that vibration switch is going to be installed, they could be shut down or still running. So fan 1 assessment. So where the Y in that ductwork split, there was a short straight run, there's differential pressure gauge, there was a zero leak damper, filter box to the inlet box to the fan. Differential pressure gauge. Now this should have been an indication to the contractor that there was a problem, but that gauge was half filled with water, and that was right upstream of the zero leak damper. Evaluating the damper in a closed position, there was signs that there was some dripping water. We cracked the damper open, and that bottom picture you'll see, we just cracked it. It was an estimated 600 gallons of water that would fill up in that ductwork up to where that Y split starts on just fan 1. And it's due to the condensation that would build up, and it would just naturally trickle down into that side of the ductwork. 600 gallons is, and fans are not designed as pumps. So what did we do? We brought the fans back in stages. So we brought fan 1 back in stages, and basically all I'm showing here is, we're bringing the fan back with no ductwork connected, okay? Because we want to see, is everything operating properly at speed? Then we connect it to the discharge and see, are we still good? And then we connect it to both the inlet as well. Once we connect it to the inlet, now all of a sudden there's an issue, right? We know based off the CFD analysis that the wheels are not loaded properly, and we confirmed that at the higher speeds we're getting a lot of turbulence. The outcome, basically water buildup, high vibration, and lack of maintenance contributed to the site problems. The air permit rewrite removed real-time VFD adjustments of speed. I mean, fans have a life cycle, but when you're constantly cycling that fan up and down with a VFD real-time, that's a lot of wear and tear on the fan. Different fan inlet and outlet conditions equals different operating points. Both fans needed to operate at a little bit different point. They added P-traps ahead of or upstream of the dampers to ensure that water was getting drained and would not build up. They reduced the airflow, the air-induced vibration by adding unistrut to some targeted areas. And then users are monitoring, and additional checks were put into their maintenance routines. So as a recap, good duct design is critical to successful fan installations. Following AMCA's recommendations for straight runs of duct between system components is a good first step to make sure the fans are going to operate as intended and that you're getting the performances. Excessive vibration is a good indication of a problem, always with a fan. Vibration disconnect switches are one-directional. Always keep that in mind. And they're only monitoring that one direction. And as I showed in one of the previous slides, that vibration can be high in one direction only. And then routine maintenance needs to be done, needs to be even done if the fan is stored, if the fan is installed, and also when it's in operation. And then proper drainage needed for low points in duct systems with humidity. Unfortunately, the fans were the low point of the entire system.
All right. So I've got a prison cell ventilation application for a facility with about roughly 200 individual cells. And each cell had a 6x6 opening in that cell that they were ventilating through, and each one of those openings had a 3/4 inch hardened bar in either direction, which is per code for the security aspect. So with this application, the challenge was the fan was not performing. They were not getting the ventilation in the individual cells that they were requiring. And then one of the other challenges is being a prison, we had very limited access and availability to the system and components. So that posed a challenge. So we troubleshooted, looked at the fan performance, the fan curves, and compared it against the readings we were getting. And it showed the fan was in surge or in install. So then we looked at the layout, the as-built design versus the duct layout, and it was a really good duct layout. So we couldn't figure out what was necessarily the cause. We looked at the fan. Can we increase the speed of the fan that's on site to get us to that pressure point or the flow required for each individual cell? And unfortunately, the fan was designed near the max RPM, so there was very little capacity left in that fan. The next thing we did, we looked at the cell and asked the contractor, can you remove one of those bars in the cell and retest? And they retested after removing one of the hardened bar sections, and sure enough, it hit performance dead on. And so it was a situation where the hardened bars took the 6x6 opening down to 5 1/4 by 5 1/4, essentially reducing the free area by 24.5%. So as an outcome, because we did not have any more pressure capacity or flow capacity in the fan, we had to replace the fan with the next size up. So, in looking at this application, the free area reduction by a 3/4 inch bar in both directions was significant enough when compounded over 200 cells to have a drastic impact on the fan. And also selecting the fan at or near max RPM or near max capacity without giving any extra plus or 10% or more capacity also limited the outcome to having to replace the entire fan. So that's just one of the things when you're looking at critical fans or systems that have a high quantity of the same system effect, just double check to make sure that those are accounted for. Because even a 3/4 inch bar can make a big impact. So then it'll take me into example 4. This is a paper pulp process exhaust application. So this was a centrifugal arrangement 8 fan with a 3/16 stainless steel airstream. It was 1,000 CFM at 60 inches of water column, designed at ambient 75, 80 degree temperatures. So it was VFD operated. The challenge came in after about 3 months of operation. This was exhibiting 0.8 inches per second vibration. So this thing was pretty much jumping up and down. The entire mezzanine this was on was vibrating. So we looked at the duct layout, the installation. That seemed to be sufficient. There wasn't any major glaring system effect directly upstream of the fan or that was causing adverse system effect. We compared the operation of the fan on the VFD to changes in the system as they were opening and closing dampers on the tissue head, pulling different vacuum pressures, trying to see if maybe one of those is pushing the fan into surge. That looked good, but in reviewing the duct layout, we noticed that the epoxy coating had been cooked off the housing of the fan. So we went back to maintenance and asked about, what had happened, and maintenance did confirm that they deadheaded a damper on the inlet of the fan for about 6 to 8 hours due to a emergency breakdown elsewhere in the plant. So they let the fan sit there for 8 hours and get hot enough to cook the epoxy off the housing. So as a result, the original fan only being designed for 75 degrees, the 316 stainless steel did not have enough strength to withstand the 500 degrees. So it warped the impeller, and that's what caused the major vibrations. So we estimated that the housing was well over 500 degrees based on the technical data sheet for the epoxy coating that was applied. So the fan was brought back, it was reworked, and the wheel was redesigned to include other stainless steel components or materials such as Inconel to increase the structural components to withstand a new design point of 550 degrees. So for this example, looking at applications where you could have a deadhead scenario because someone closes a manual damper, making sure your fan can run to that 500 or whatever deadhead temperature it is, or possibly putting in temperature sensors, flow sensors, or vibration switches, like Ryan had mentioned, that would catch that excess of vibration and then shut the fan down prior to letting it run for 8 hours. All right. Justin.
So our fifth example has to do with elbows, tees, and control dampers that can be put into a combination that will cause poor inlet conditions at the fan. So what you see down below is a system where it's running with, we have 2 fans, one's running all the time, the other one's in standby, and they alternate back and forth. So the air comes down to this T, and there's 2 isolation dampers blocking, that block off the fan that's not running with the air going into the fan. So we found out in this case, so the T's and elbows, they can be problematic anyways. The air kind of comes down the main duct and then it hits the bottom, and then most of the air wants to go to the outside of the duct. So they really help to prevent having good consistent flow at the fan. So in this case, the customer called in, they said the fans were loud during operation, and they're also vibrating. So we did some analysis, and then the top example is how these fans were intended to run with the air coming down the main duct going around the elbow with the isolation damper fully open. And this isn't the greatest setup to begin with, because as the air is coming down the duct, that damper serves to hold that air in the bottom and prevents the air from spreading back out and becoming even. So FEA analysis showed that about 30%, that the velocity gradient changed about 30% from the top of the fan discharge to the bottom of the discharge, with the highest velocity being at the bottom. The system was also operating at a lower pressure than what was initially required, so the system was moving too much air. And in the bottom example, what the customer had actually did was to use that isolation damper as a control damper, and they closed it about 45 degrees in order to get the airflow down to where they needed it. And that just makes the whole system worse. It just traps more air at the bottom. You can see the lines, a lot more turbulence, and feeds the wheel unevenly, and it was actually causing vibration. The levels where welds were cracking in the wheel and on the fan housing itself. So the solution to this issue was just to add a VFD to the system to slow the air down, to slow the fans down instead of using that isolation damper. Apologize, we switched up who was doing what. So yeah, just when you thought we've seen everything, and Ryan actually took this picture. So this was an issue, they had a footprint issue with the fan. And I believe the fan was ordered in the incorrect orientation, so they kind of just made it work. And it's kind of one of those pictures, the longer that you look at it, the worse it gets. They took the inlet box off and put it on the outlet to use it as a kind of squared around transition. The fan itself wasn't in good shape, a lot of vibration. I think Ryan said he was afraid to stand there to take the picture of it when it was running. So this is kind of one of those, if the fan's not the right orientation for where you need it, it's like this just do it right not to do this. Then another good example of this would have been to use a square inline centrifugal style and have the fan, have the discharge and everything go in the right direction. So,
Yeah, that was, when I saw that blew me away. So example 6 is a wastewater odor control. Now this is a complex system with fans in parallel, series, and both. Centrifugal belt-driven fans with odor control fans on VFDs. We had 6 supply fans, 12 exhaust fans, and 2 operating plus 1 standby odor control fan. There were 6 branches that feed at various points in a common odor control header. And then overall airflow wanted was 91,000 CFM. And the system was brought online in segments, beginning with the odor control fans. And then airflow was being measured between branches 3 and 4. And then they would just tack on basically what they assumed the other fans were going to be adding to the airflow. System layout. It's a push-pull system operating with fans in parallel and in series. I have a diagram there. There's 6 stages of branches where the fans are feeding into to come up with the 91,000 CFM. And interaction between stages 1 and 6 are basically where they're operating in series and parallel, and then the interactions of 1 and 6 with the 7th stage is expected as if it's in series. So a very, very complex system. A layout. So as you'll see on the top left, the final 3 branches, and then bottom is where the odor control fans are. Not ideal conditions. You really never want mitered elbows to begin with, and having elbows in sequence can be very, very bad. And then the far right is the overall system. So it's a very large system, and a lot of branches, a lot of things going on. So some of the background is balancing prior to shipment, BV4, AMCA air performance tested, all the fans. Odor control fans started 6 months after installation. The supply and booster fans were installed and started up between 1.5 years to 2.5 years after installation. All fans lack PMs. I feel like this is just a recurring thing in the job sites. But systems brought online in stages over a 1.5 year period. So some of the challenges and troubleshooting steps. So it's a complex system with fans brought online in stages. Contractor did not have air balancing done. They actually waited until there were problems. Poor maintenance and operation. We had erratic airflow proceed because of duct configuration. High vibration on odor control fans. Actually, the oscillating vibration on odor control fans 1 and 2 was severe at times. Extremely noisy. Frequent vibration trips. Odor control fans 1 and 2 and 3 all would trip at times. So it's a +1 system on the odor control. And then the troubleshooting, verify the fans operating in a good point on curve. We checked the VFD history, see the airflow, hertz, amps, etc., and then field evaluate all fans. Site walked, to see all the conditions. Fans checked to ensure not in a bind, because they were all rigid mounted, not on vibration isolators. Bearings were checked. Vibration readings were taken on all fans. All PMs were brought up to date, and all bearings showed signs of basically under-greasing. Airflow and pressures monitored and then the airflow and pressures were monitored at the odor control fans to see if there's some variations. Vibration. So this was really eye-opening to me, is that there was axial oscillating vibration cycles that were characterized by, basically it would come into focus over 15 seconds and go out of focus over 15 seconds, that vibration. We could hear it ahead of seeing it on the meters. The odor control fan bearings deemed in need of replacement. So when we pulled the bearings, the shafts on the drive end were turned down, and that picture is actually a picture of the shaft, and it was turned down due to the oscillating vibration. Bearings replaced with concentric bearings to try to counter the oscillating vibration, and then shafts for 1 and 2 were replaced because of the turn down. The outcome in bringing the system online in stages is highly recommended to air balance each time a fan is added. System pulses can occur when airflow is not balanced. Once full system was air balanced, all vibration issues were resolved, which is kind of eye-opening to me because of the duct layouts and how many double elbows and such that we saw. Contractor did not want to air balance up front until all the fans and branches were finished. But bringing the system online and not performing air balancing often results in problems, even when one fan is involved. As a kind of a recap, air balancing should be performed anytime fans are brought online, especially in a complex system where fans are pushing, fans are pulling, and they're interacting with each other. As I said before, fans in series and fans in parallel, they have different properties of what they do. And so if some are sharing airflow and some are sharing pressure, it becomes very difficult to balance a very complex system like that. Left unchecked, oscillating vibration can cause turn down on fan shaft because the 316 stainless steel shaft versus the bearing seats, which are hardened steel, that hardened steel it's harder than the stainless, and therefore that airflow profile, that oscillating vibration would just naturally cause it to turn down over time. Good duct design, providing laminar airflow helps to avoid this. If the duct was designed without the elbows and such, and it was better designed, I think that the oscillating vibration wouldn't necessarily be there in the first place. And another good indicator of unbalanced are airflow readings outside the expected norms. They wanted 91,000 CFM, but it was erratic at best, and they would fluctuate anywhere from 85 to about 96,000 CFM just over the course of seconds before the system was balanced. Right. And then we wanted to open it up for questions. Anyone? Oh, go ahead.
Well, thank you. Very good presentation. I'm Carlos from Sigflux in Brazil, and I'd like to know if you have any experience with fan walls like plenum fans, which doesn't have any housing and any duct. So if you have anything to tell about this.
In regards to plenum walls in like an N1 plus configuration, I have a little bit of experience on the commercial side. Do you have a specific question?
My question is related to the system effects, because you have 2 or more rotors without housing, and if there is any consideration or any way to calculate the system effect that one gives to the other, you know?
That's a good question. There are instances where if you have a fan that's not operating, if it doesn't have a anti-backspin or a brake on it, you could backspin a wheel. And then if it does start, that can cause adverse system effect or can cause fan failure. Fans in close proximity to each other you can have fans steal air from another fan. So you'd have different performances within a, like a 3x3 fan array. You could potentially have different performances relative to an elbow or a transition upstream. If you've got a 90-degree elbow without turning vanes, you're going to have a higher load on some of the fans versus the other fans. So that, again, comes down to duct layout, duct design, and then testing and balancing across that entire array.
My name's Chris from Integra. I'm a balancer. One of the things that you just touched on with the with the shaft turndowns in airflow, if you can expand on, the pulsation and how that may affect, fan shafts, bearings. We have a situation, one where they just keep replacing bearings on some of these fans, and they don't know why. So they just continue to replace these bearings, and they continue to fail. And they haven't actually come up with any kind of, solution.
I've run into situations where you've got a high axial load on the. Someone else. So the question was to elaborate on bearings and turning of the shaft or replacing bearings on a common basis. That can be due to an uneven load on the wheel. So if you've got majority of the airflow coming in and hitting a fraction like a quadrant of the wheel, now you're putting an uneven load on those bearings. It could be a high axial or a high thrust load on the bearings as well. So that's another thing that can cause premature or side loading on a bearing that's meant for a radial. So if you've got a spherical roller bearing or a heavy duty roll bearing and you're putting a high axial load on it, that can cause premature failing or too light of a load if the bearing's skidding. So if you're not getting enough loading on that bearing. So those are a couple scenarios that can cause premature bearing failure.
I'll add to that. So in the picture right here, so the odor control fans there at the bottom left, what you're going to see is there's more or less like a double elbow that creates a corkscrew effect. And technically speaking, the airflow is also rotating in the wrong direction once it hits the wheel. So therefore, that oscillating vibration is driven by how that airflow is interacting with the wheel. And that was causing the oscillating vibration. Once they slowed down and got everything working properly, it got better. But they still monitor it, but it's not beyond the levels of shutdown, but it's still present. They can't get rid of that oscillation vibration just because of how that duct layout is and the rotations of the airflow. Any other questions?
So for design engineers, is there a tool other than CFD analysis to help better predict when you'll encounter this effect? And how it would account for those losses?
So the question is, is there tools to better account for the system losses and stuff? Yeah. So what I always say is per AMCA. Now this is per AMCA, per their system effects. Ideally, so when you have those system effect factors that you're using as an engineer to account for losses, it's assumed that whatever, if you have an elbow or you have a damper or whatever else, that you have straight runs of duct between or before and after that. And I think they say 10 duct widths of length before and after is what that factor is based off of. So CFD does give you a very good idea, but outside of that, it's just following the standards that are out there, like per AMCA and ASHRAE. And honestly, what I see is is that engineers have told me, well, we account for the losses. Well, when you have double elbows, you have a T that feeds an elbow, or you have a damper right in front of the fan, you can't account for that interaction on the fan and how it's gonna impact that fan. And so, you know, you really just having straight runs before and after anything in the airstream before the fan is kind of critical, the critical aspect of it. And footprints are getting tighter and tighter sometimes, and when you got really tight footprints, when we really see issues. Anything to add?
Yeah, because a lot of times you can't design the perfect system. I mean, you're limited on footprint on space and things. So even things like turning elbows, turning vanes inside of the elbows can make a big difference. Straighteners, things like that can also help eliminate that problem.
And slower airflow. I mean, we've seen systems where feet per minute can get up to, let's say, 5,000, 6,000 feet per minute, and all of a sudden the silencer is failing because the airflow is too fast for it, and it's shooting pins through the walls. So, any other questions? All right. Well, thank you.
Thank you for your time.